And good morning and welcome to Chapter 2. Today we're going to talk about LAN redundancy. And in LAN redundancy, we're going to cover primarily two things, the spanning tree protocol and HSRP, the hot standby routing protocol. So we'll talk about how we can make sure we have redundant links just in case a link goes down and another link will automatically pick up if there's a connection. So this way you don't lose connection between the two switches. We're talking about trunks. And we're also talking about another router sitting on the side in case your router goes down for whatever reason. So another router will pick up immediately, so you will have a connection to your default gateway regardless. If it goes down, another one will pick up immediately. That's when we're talking about the HSRP and the GLP towards the end. And we'll be able to do packet traces. So I'll be asking you also questions, during the lecture, and you have to answer those on a separate sheet of paper. And with that, by the way, you can answer those questions with chapter one. Chapter one, and no, do it separately. Yeah, each chapter should be separated by itself. So the questions that I ask with chapter two, just put them on the Microsoft Word, and then you'll do the packet tracer as well. You will submit that as well for your homework. Okay, let's get started. So let's talk about the spanning tree protocol and what is it used for. Well, when inside a LAN, when we're sending data from one device to another, data has to go through a switch, and a layer 2 switch, all it looks at is the frames. And all it needs to do is just look at the destination MAC address, find out where that destination MAC address is located, which port, and then send that frame um, to that port. Okay. Now the problem is what happens if you don't have redundancy. Let's say you have two switches and you lost a link. First of all, then you won't have any connections between the two switches, like when we created VLANs last semester. So if you just go ahead and create and put another trunk, let's say two trunks, just in case. The problem with layer 2 switches is they will try to send data out of both. They'll use both trunks to send the data out, and that's a big problem because on the receiving end, the switch that is receiving the two, from two trunks receiving data will be able to send the data to all, for example, they'll send the same data that's coming from both trunks to the same destination. That's called multiple frame transmissions. I don't want to be able to receive, two frames, the same frames from the same source. So that's not a problem. That's a big problem. Also, if somebody sends a broadcast frame to those two trunks, then the two trunks, they send them to the other switch. And when this other switch receives the broadcast storms, they send it to everybody else and it becomes a mess. And they just keep sending broadcast frames to each other. All right. And the MAC address table it's all going to be screwed up. So therefore, just adding another trunk on the network between the two switches, it will create a problem. You need a software that is going to say to be able to recognize that there are two trunks and only use one of the trunks to transmit and receive data. The other trunk will just be sitting idle just in case something goes wrong with the primary trunk. All right, now at layer 3, thank God there is something called the TTL number, the time to live, that is stamped on every packet that is released. And that time to live field that is stamped on the packet, every time that the packet goes through a hop or a router, that TTL number is decremented by 1. And that number is usually 255, which is an 8-bit number. If you did not reach your destination before that reach your destination, the TTL number reaches 0, then the packet is discarded. It's thrown in the garbage. We don't have that kind of thing on a frame. Switches can pass frames from one switch to another forever. There is no TTL number stamped on the frame. So that's a big issue. Frames can loop. That's what looping is. Can loop around between switches looking for a destination and that it doesn't exist. So we gotta solve that problem at, at layer 2. Okay, inside the packet, inside a LAN. All right. So a broadcast storm, like we discussed before, if somebody sends a broadcast storm, and that broadcast storm can, if you have multiple trunks, it will jam the network within seconds, less than seconds, and it will bring the whole network down immediately. No one will have access, in other words. So STP resolves that problem. Okay, so here's some broadcast storm. Let's say PC4, wherever PC4 is, sends out a broadcast storm. Broadcast storm comes out of here, then this sends it out to here, then this guy sends it out to everybody, and also sends the broadcast back to 0, 1. And what does he do when he receives a broadcast? Sends it back again, then he sends it back again, and another broadcast comes back again. And so you just these switches keep broadcasting to each other, and no one else will be able to communicate, right? Duplicate frames, be sending the same frame twice. So this PC1 wants to send data to PC4. A frame will go out of here and come to PC4 and also will travel this way and get to PC4. So we don't want the same frame coming to PC4. Okay, so that is not good. Okay, so what does the STP does, the spanning tree protocol? Well, it takes care of the broadcast storms. It's going to take care of the duplicate unicast frames. And the way to do that is to make sure that it's going to take out all the links that are on the network and just pick one link that goes to the destination and let the others just sit idle. This is really just a quick explanation, but we'll get into details in a few minutes. So that's basically what the STP does. Think of it this way. It's like what the routing protocols like RIP, EIGRP, or OSPF do at layer 3. They find paths for the packets, and if there is a problem, they reroute them. STP works like that for layer 2 for the switches to make sure there's only one best path to get to the destination, and if there's a problem for that path, they are going to reroute the frames from one switch to another till they get to their destination. This will avoid the looping, the broadcast storm, or the duplicate unicast frames being sent to the same destination. Okay, so here's a typical connection. So if you run STP on these 3 switches, one of the ports ultimately will be blocking data. No data will be going in and out of this switch 2. So data will only travel this way and go to the destination. Even though another frame will be coming this way, ultimately it's going to get blocked right here. So no data will be traveling back. So this will be a blocking port. So really data only is going this way. Now, if something goes wrong and this link breaks for whatever reason, either the port or the links, any of these 2 ports or the link, then the switches will ultimately reroute, open up this port, and then the data will travel this way. And we're talking about milliseconds. So it's really transparent to the devices. They don't even see that. They don't even actually sense that there's a problem connection-wise. Okay, so how does this work? What happens is all the ports on the switches, as we will discuss later on, they have a role. You act either a designated port. Designated port means a port that is allowed data to go in and out. Okay, first of all, the first thing that's going to happen is the following. Well, let's discuss that. When you have multiple switches in a network and STP is running and you have trunks, in a mesh connection, whatever, what they do is they will elect a root bridge. Instead of everybody's trying to go different ways to get to the destinations, what they do is they say, okay, we're going to elect one root bridge. And once that root bridge is elected, all the data goes to the root bridge. So no matter where my destination is, I will send the data to the root bridge, and then from the root bridge will find me my destination. So regardless of where you are. So if let's assume S1 was elected as the root bridge. So what you're going to do is S2 will find a port that is closest to the root bridge. So you'll connect it to that bridge. S3 will be connected to, he'll say, my 01 is the quickest way to get to the root bridge. So that will be, send that data, that port will be set up as a root port. So a root port is a port that is connected, is the fastest port to get to the root bridge. That will be forwarding and receiving data. As you can see on the root bridge, you have both ports, both trunk ports have to be designated, open up to receive data. The non-designated, then these two ports, then they have to negotiate and say, hey, listen, one of us has to block data. So when they negotiate, this turns out to be the one port that is going to be designated, and the other one is non-designated. And by the way, it doesn't matter if he's designated. He sends out the data, it's going to get blocked here anyway. Okay, so just a quick review. Designated port, root bridge is the root bridge where all the data is sent to. And then from the root bridge, you get to your destination. That's number one. Now, each non-root bridge means like a switch, by the way. Each non-root bridge, they have to find one port, configure one port called as the root port, and that root port is the quickest way to get to the root bridge. So for S201 is the root port, and for S301 is the root port. And the other ports are either could be designated or non-designated. Designated port means data is allowed to go through. Non-designated means blocking. Okay? Let me give you an analogy so you'll understand, because this is a little bit more difficult to really comprehend. A little bit more difficult than the others, at least. Let's say all the big states in the United States are bridges, switches, right? And we are all interconnected, so you can get to every state in from different highways. I'm just going to make up highways. So uh, let's say I live in New Jersey and I want to go to, I don't know, Florida, or Florida is another switch. There's a trunk, Route 95 takes me to Florida. Um, or I can use, so all of these states, they want to go to different destinations. So what we're doing is there are multiple ways to get to Florida. I mean, you don't have to take Route 95. You can, there are multiple highways that will ultimately get you there. But Route 95 is the quickest, right? But because there are multiple highways, because I'm sending data out, data will try to use every highway to get to Florida, and that creates a problem. So what STP does is it tells all the states we have to pick one state as the root switch, which means no matter where you are going to go, no matter what state you are from, you're going to go to that one root bridge state. So let's say after the election, all the states, all the switches talk to each other, and we elect, let's say, I don't know, what's the state right in the middle? Let's say Nebraska. Nebraska is the root bridge. It turned out it won the election. So if I'm ever going to go to Florida, I have to first of all, forget about Florida for now. Now, once Nebraska was chosen as the root bridge, then I have to find a highway, the quickest highway to get to Nebraska from my home. Let's say it's highway number, I don't know. I don't even know. There is no highway to get to Nebraska. Number 5, right? So out of New Jersey, my port that gets me on Route 5 will be called a root port. In Nebraska, that Route 5 that connects to Nebraska, that port that enters Nebraska, the route bridge, is called a designated port because it allows data to come in, right? So this is like Nebraska right here, and this is New Jersey, and this is Route 5, right? Another state, so let's say Wyoming, has another highway to get to Nebraska. Everybody has to go to Nebraska, and then from Nebraska, you go to your destination, okay? You don't use any other route. No matter where you're going to go, you have to go to Nebraska. Is that clear? So if I wanted to go to Florida, even Florida is closer than going to Nebraska than Florida, I have to go to Nebraska. And then from Nebraska, I'll go to Florida. They'll find me a route. That's how STP works. Is that clear? All the other highways will be sitting idle in case my connection, that Route 5 to Nebraska, goes down, and then STP will find me another route, all right, to get to Nebraska or another designated route. So that's pretty much how it works. So from California, you'll be going from one, you'll go to Nevada, for example, and I don't know, maybe from Nevada to Colorado, switches and so on. So Nevada will have some designated ports to allow California route port. If you can imagine that, Nevada has to have a designated port so they can get through Nevada to get to Colorado, and from Colorado all the way to Nebraska switch. So no matter if you are in California and you want to go, no matter where you're going to go, you have to get to the route bridge, and then from the route bridge you get to your destination. All right? Sounds good? Now, Nebraska, all the highways coming into Nebraska have to be designated. That means none of the ports, none of the trunks, none of the highways that are coming into Nebraska should be blocking data. They all should be open to receive and send data. Is that clear? So if you ever got a topology and they asked you which of those switches are the root bridge, you really look at the trunk ports. That's a quick way of doing it. If you look at the trunk ports, if they are all designated, you know that that is the root bridge. Okay? And it should not have any root ports because it's a root bridge. Why should he have a root port? It's himself is the root bridge. All right, let's continue. So now you have a better idea of how it works. So how does the election work? Every device, every switch, assuming we only have, there's one LAN in every switch. So every switch has a MAC address. VLAN 1 has a MAC address, and they get a priority number. So a priority number is attached right next to the MAC address. So here's the MAC address. This whole thing, this whole 16-bit is really, let's for now call it the priority number, which is the bridge, the bridge priority and the extended together. When you attach these together with the MAC address, this is your bridge ID. So every bridge will have an ID. Okay, your MAC address plus the priority number. The default priority number for the switches is 32769. Okay, so what we do, the first thing that's going to happen is we have to send out your bridge IDs to each other, and all the bridges, all the switches, I keep calling them bridges. It's really, okay, anyways, it's a switch. So all of them, they have to negotiate, they have to look at the bridge IDs, and they pick the guy with the lowest bridge ID. Okay? By the way, if everybody has the same priority number, so the first 16 bits is 32769, and if everybody has the same thing, remember this is the most significant part of the bridge ID, so it really comes down to your MAC address. So the guy with the lowest MAC address number wins. So for example, this guy, because he has an 0AA1111, is lower than this guy and this guy. If all three switches have the same priority number, switch 2 would have won. 1 means he would have became the root bridge. But we can manipulate, we can change the priority number from 32769. This, we dropped it to 2457 here. So if we dropped the priority number on this switch, his bridge ID is going to be lower than switch 2. So when the election occurs, that's why switch 1 was chosen as the root bridge. So that's what we're going to be doing. We want to know it. We want to make sure strategically or manipulate the election to make sure that one switch wins. And how can we do that? By lowering the bridge, the priority number, so that that switch will have a smaller or a lower bridge ID. Okay, and therefore we'll make sure and we'll force that bridge to win the election. Okay, so after the root bridge have been elected, then we have to choose which is the root port. In other words, which highway to get to Nebraska, which is the best highway. So you look at all the bandwidth, the speeds on the highways to get to Nebraska. You know, the switch one is Nebraska, right? So if this path is, 70 miles an hour, this is 70 miles an hour, this is 70 miles an hour. So the best way is to go through port one because it's the shortest distance. Why go through two different cities to get to the root bridge when I can go directly to it, right? Each trunk, depending on the maximum bandwidth, maximum highway speed, is assigned a number called the cost. So if this path, this highway is a 10 gigabit, he's going to be assigned the number 2. If it's 1 gigabit, it'll be assigned 4. So what you do is, for example, if this trunk is 100 megabits per second connection, right? And this trunk is a gigabit, so this will be assigned the number 19 because it's 100 megabits. This one will be assigned 4 and this one will be assigned 4. And after the root bridge has been elected to choose a root port, then I will choose this path because 4 plus 4 is 8. And it's quicker to go through this way than to even go directly because this cost me 19. Is that clear? But if all the trunks have the same cost, then the shortest distance, of course, is the quickest. Okay, so that's how root ports are chosen, by looking at the cost. You can actually change the cost number if you don't like this. You can increase and decrease the cost number. Okay? So these can also, you have control over them as well. This is the frame format of the bridge protocol data unit that is being sent between bridges to negotiate for a root bridge. And this is the bridge protocol data unit propagation and process. This is really the elections that is being occurred, right? So the first thing that you should do is change the bridge ID on a switch and leave everybody else the same, leave them the defaults. And when the election occurs, they start talking to each other and comparing the bridge IDs. They will ultimately pick the one with the lowest bridge ID. Okay, so by the way, remember this. If you remember last semester when we talked about OSPF, in OSPF, there was a negotiation for the designated router, and we manipulated the election by changing the priority numbers on those OSPF router ID numbers. Now remember, with OSPF, the guy with the highest priority number wins and becomes the designated router. Here, the guy with the lowest priority number wins. Is that clear? Wins the election and becomes the root bridge. This is how I remember it. OSPF is layer 3, so a higher number on the priority wins. STP is layer 2. A lower priority number wins the election, right? All right, so here's your bridge ID, your MAC address plus the bridge priority number, which consists of two things. The priority number plus the VLAN, really, that's what the extended ID is, which we'll talk about later on. The election, if you have one switch that has multiple VLANs, for each VLAN you can have an election, right? So we talked about the analogy before, all the states. Each state is one local area network. That's what it was, right? But imagine, like, let's say every state has multiple VLANs. So, for example, you could have an election that picks Nebraska for VLAN 1. So, for everybody that wants to go to VLAN 1, Nebraska will be the root bridge. For example, if everybody in the Northeast has VLAN 20, so it's probably a good idea to pick a root bridge for VLAN 20 in the Northeast. So you manipulate the election for VLAN 20 so that, let's say, Pennsylvania will be picked as the root bridge for VLAN 20, closest to the Northeast, right? So when STP runs, it's going to look at all the VLANs that are on the bridge, and then a separate election will occur for each VLAN. That's called per VLAN STP. All right, so that's what the system ID, the bridge ID is for. Again, the default is 32.769, but we can change that number. Okay, here are different varieties of STP. The original one was created in 1998. That's the IEEE 802.1d. Cisco has the per VLAN STP plus, which means an election will occur for each VLAN separately. Okay. 802.1d 2004 is an enhancement to the old 1998 one, which allows for still much quicker convergence when the link goes down. Rapid STP has a much better the one with the W subscript. Okay, so that will allow the convergence to go much quicker. Now Cisco PVSTP Plus is really an enhancement to the old PVST that also done for really quick convergence. So when the link goes down, in milliseconds, you'll be rerouted. So it's really transparent to the users. All right. By default, all Cisco switches run PVST plus. So all the trunks by default are running STP. So this way to make sure that you don't get into any problems. All right. So the Cisco proprietaries are the PVST plus and the rapid PVST, as you can see. The MSTP, the multiple spanning tree protocol, this allows for per VLAN STP, just like the Cisco one, but it runs on multiple. Most of them are really can run on Cisco. The enabling this is easy as well. So the configuration wise, it's not that bad. Okay. Um, Even though the convergence is slow, PVST plus is the default, but you still need a high resources, a lot of resources in terms of memory utilization and CPU power. Okay, and you probably want to do per VLANs. That's why it's the preferred. I don't know. It's not that bad. I mean, configuration wise. All right, so here are some characteristics of PVST plus per VLAN STP plus. So there again, for each VLAN, you create an election. So you pick a root bridge for each VLAN. So not a lot of traffic wise, it'll be more optimized. You can have better load balancing. Okay. So again, for VLAN 10, you create an election. For example, he may be the root bridge for VLAN 10, and he may be the root bridge got elected for VLAN 20. So if for switch 2, if he has VLAN 10 and VLAN 20, if he needs to send data to VLAN 10, which is on the switch 3, he has to go to S1 first to get to S3. If VLAN 20 guys in here want to send data to VLAN 20, it has to go to S3 first because that's been elected as the root bridge. Okay, so this is a lot more efficient way. You do some load balancing between the switches. You don't want S1 to be um, the spanning tree for all the VLANs, although you could do that if you want to. Okay, now The ports on a PVST, they go through five states, as you can see. So this is a typical question that comes up a lot on the STP. What are the five states that STP can be in? Number one, you could be blocking. If you are blocking, no data goes in and out. So when you first turn the switch on, the switch goes into a blocking mode. Then it goes into a listening mode. Okay, allows data to come in, but it's not forwarding data at all. Okay, not sending and receiving data. He's not learning any MAC addresses. He's just listening, and this is when the elections are occurring. Learning is when you start learning MAC addresses. Okay, the election has finished and you're trying to build your MAC address table. Forwarding, that means you're already, the link is green, blinking green. It's forwarding and receiving data. Okay, so you have to go through three states before your ports becomes forwarding. Now, if it's disabled, that means an administrator must have went to that interface and typed the command shutdown, right? All right, I'm not asking you any questions, so I think let's ask number one. Question number one. So let's start. What are the different roles of the ports for STP? There is a root port, designated port, and non-designated port. Okay. Do me a favor. Explain to me without me doing anything. Can you explain what a root port is, what a designated port is, and what is a non-designated port? Explain what those are. Question number two. Okay. How can you manipulate the election to make sure a specific switch wins the election? And the answer is, I'll tell you the answer, by lowering the bridge priority number so that a specific switch will have a lower bridge ID. And when the election occurs, the switch with the lower bridge ID wins, right? And what is question number three? What is the default priority number? It's 3269. 32269. Okay. Just 1 second. What did I say? 32768. Okay. All right. So rapid PVST, which we're not going to configure, but it's easy really to do it configuration wise. We're not going to do it in the lab. There's a certain way you probably can do this, and the commands that you can see, I'm going to show you what commands to do to activate rapid PVST plus. Okay, to allow, this is for quicker convergence. So rapid supports the new port types, alternate ports it's called, which means, the port just stands on idle. If one port goes down, immediately will, if the root port gets disabled for whatever reason, the alternate port takes over immediately. Okay, so there is really no negotiation. So that one makes it pretty good or pretty fast in convergence wise. Okay. So rapid STP, you have pretty much everything is the same thing. This will be an alternate port, which means I will immediately go into designated if this trunk fails. Otherwise, the ports are pretty much the same thing. They have the same designation. This is the bridge protocol data units. This is the labels that are on all the frames that are being sent back and forth when you are, negotiating between the two switches. Okay, edge ports. Edge ports are ports that are attached to devices such as hosts, and they are not trunks. There is no reason that these two should go through blocking, listening, learning before they start forwarding. You want, when I connect a PC to this switch, He's not a trunk. I want it to turn green immediately. I want it to go to forwarding state very quickly. And the way to do that, you go to that port right here and you say, you are going to be PortFast. So when you type that command on that interface, you're telling it to really disable STP. Okay? So edge ports, you should write the command spanning tree PortFast, and that pretty much disables STP. But you got to be careful if you're ever going to use these ports again, use them as a trunk. Remember, STP has to be active, so you have to type the command no spanning tree PortFast to bring them back into the dynamic so they can go through the 4 states, the 5 states: blocking, listening, learning, and forwarding, right? Okay, so the link type, again, you can either have the edge ports right here, root ports right here that connects to the root bridge. These guys are designated, and this is the alternate guy, the blocking, right? Now we call them alternate for PVST plus. Okay, so now we're going to get into the configuration. Configuration-wise, it's very easy. All right, PVST plus is the one that is by default. Rapid and MSTP are disabled, but we can enable them in a second. Here's the switch priority number, 32768. Okay. By the way, if when the negotiation happens, you're going to have for VLAN 1, you add a 1 to this, which will show you when we're doing the configuration. The port priority number, the default is 128. Here are the link and the costs for each link so that then the negotiation happens. The timers for the spanning tree are all right here. Those are the defaults. And usually we don't play around with any of this. Okay. The only thing that we can change is we should play with is the switch priority number so that, again, to lower it so that you can manipulate the election. Now, how do you configure our primary, our number one job is to force the election or force a specific switch to win the election. So I can go to switch 1 right here and say, hey, spanning tree for VLAN 1, you are the root primary, and then, or you could do it by, and then go to this switch and say, you are the secondary, okay? Or you can use it using a priority number. So if you don't like to work with numbers, you just say root primary, root secondary. He's going to be the backup to the root bridge, which is S1 would be the root bridge. Or another method is by saying, hey, switch 3, your priority number is 245676. Now, because all the others are 32768, they will lose the election, right? I'm telling you, on CCNA exams, a lot of times the priority numbers come up, and they are increments of 4096. You don't increment or decrement the priority number by 1 or 2. They are incremented and decremented by the number 4096. The lowest priority is 0, and then you start increasing by 4096. Okay? So when you type show spanning tree, it says this is the root bridge. So now you know that S3 is the root bridge because of this statement. Or you can tell by looking at the interfaces, the trunk ports, fast Ethernet 01 and 02, and you see they're both designated. Remember I told you earlier that if all the ports are designated, then you must be the root bridge. You look at it, his root ID and the bridge ID are the same. This is the priority number, and that's his MAC address. Now, because it's for VLAN 1, it becomes 77 with the extended ID. From 24576, you add a 1 because it's for VLAN 1. If it was for VLAN 10, you add a 10 to this number. That's why his priority is 24577 because of the priority number 776 plus for VLAN 1. The system ID extension is 1. Okay, now you want to make sure that these ports are PortFast. So you go to the interfaces, you say spanning tree PortFast, which means, excuse me, they will immediately go from blocking to forwarding because they're connected to PCs. Also, by the way, you want to make sure that if this is a troublemaker PC, let's say PC1 is a guy that he will run a software and he wants to make himself look like he's a bridge. He wants to negotiate with the switch and he wants to become the root bridge, screwing everything up. To make sure to prevent that, excuse me, you go to those ports that are not trunk and you say spanning tree BPDU guard enable, which means, excuse me, if anybody's trying to send um, a bridge protocol data unit to negotiate with this switch to become a root bridge, this is going to be disabled. That means he is really an attacker. Okay, so the BPDU guard makes sure that non-trunk ports do not negotiate for for root bridges. Okay. Okay, so he's for load balancing. You want to make sure per VLAN STP, don't make one switch as the primary um, root bridge for everybody. So spread it out. Maybe switch one will be the root bridge for make an election for switch one. Maybe he will be the root bridge for VLAN 10, and he'll be the root bridge for VLAN 20. So you could do that with these commands. Root primary, go to the switch. So you go to switch 3 and you say spanning tree for VLAN 20, you're the root, and you are going to be the root secondary for VLAN 10, and so on. That's the easiest way to do it. Or you could do it by, again, changing the priority number. This is the lowest number that you can give, right? 4096. Okay, so you can tell by typing the command show spanning tree active, that's going to show you who's the root bridge to verify who is the root bridge, and it shows you the bridge ID, it shows you the ports, right? The trunk ports, if they are designated, forwarding, root ports, and so on. Show run does that too. Okay, shows you all the spanning trees and what the priorities on that switch is. So this specific switch 1, for VLAN 1, he has this priority. For VLAN 10, he has that. For VLAN 20, he has that priority number. So all of those for different VLANs, right? Excuse me. Rapid PVST, all you have to do is type these commands, and then you'll enable Rapid PVST Plus, right? So if you go config T, you do spanning tray mode rapid PVST, go to a specific interface, a trunk interface, and you type spanning tree link type point to point and then you clear the spanning tree detected protocol. Make sure you clear all the detected STPs so that the rapid STP takes over. Okay, so again, you can use the commands to analyze STP to make sure troubleshoot it. You can use the show CDP neighbors. You can use a show spanning tree VLAN like we did before. Okay, to verify the root bridge, to confirm the layer 2 bridge as well, layer 2 path. These two commands we use extensively. The show spanning tree VLAN. All right. So here's if you have a problem right here, this is a blocking mode. This is a blocking mode. This should be forwarding. It should be forwarding for VLAN 100. So you want to make sure that everything is the way it's supposed to be. Okay. You can test it by looking in. This should be amber colors, the orange colors, the blocking ports. The forwarding ports should be the green, right? And as you can see right here on switch number 1, and switch number 1 is right here, all these three are forwarding. This port right here is the root port, as you can see, TE91, whatever. The Giga 3.1 and 3.2s are forwarding, right? Designated. So you know that this bridge S2 is not the root bridge. Why? Without even looking at any of this, because all the ports are not designated. He has a root port, right? The cost is 4.4. That means two. This port is a gigabit Ethernet, right? And 4.4 means this port and this port are 1 gigabit Ethernet connection, right? The 128 is the priority number. Dot 72 is this is port 72. This is port 80. This is port 88. Wow. Oh, the root port is the port 88. I'm sorry. This is port 88. And one of these two is the 80 and 88. This is the port number, fast, gigabit, whatever. All right. Anyway, what happened when you have failure? They will immediately reconfigure themselves. Any frame that is flooded on the switch enters into a loop. You don't want, data being sent back and forth. Okay. The way to really fix, if you let's say you have an edge port and you connected it as a trunk, then you're immediately go into a little bit of a loop. Now, if you ever encounter that, that means somebody is complaining and says, "Hey, all the users are connected to a switch are complaining," and you notice that you suspect there's a loop. You start unhooking the trunks till once you hook the one that created the loop, then all the users should have access to the resources. You should be back to normal. And then you got to bring everything back. Make sure you have redundancy, right? That's the best way to repair a spanning tree problem. Okay, now that's what that. Well, we're going to do a packet tracer in a few minutes. So now let's talk about the first hop redundancy protocol. These protocols allow you to have a standby router. So for example, let's say this is my default gateway. What happens if it goes out? Then I won't have access to the outside world. So what the first hop redundancy protocols do is it will have this router waiting in case this router goes out for whatever reason. I can go to this router and use that as my default gateway. Isn't that nice? So you have a standby router that if anything goes wrong with the primary one, the other one picks up immediately. All right, so here's a typical connection. So what you do is you create a virtual router, virtual default gateway, and you choose which one is going to be forwarding to the outside world. You'll see that when we do the configuration. And your PCs pings that default router, which is a virtual interface, but when it gets there, it will just go to the one that is the one that you activated. If that activated router, physical router, these two are physical routers, right? And this one is the shared, the virtual, which is going to be configured on both of them. So this virtual says, I'm going to use this physical router to send the data out. If this physical router goes out, then the virtual router, which is configured on both physical, will go to this guy if something goes wrong, right? Okay, there are several first hop redundancy protocols. There's the hot standby router protocol, the HSRP, and there's one for the typical one for V4, and there's another one for V6. They're pretty much the same thing. It's just for different IPs. The virtual router redundancy protocol version 2 and version 3. Well, we're not going to do that. We don't have that. We're just going to use this. I think we're running the version 2. You can't really tell the difference. Version 3 is for the IPv6. It's an updated one. The gateway load balancing, what they do is instead of just using one of the routers, since the other router is already sitting idle, why not just use both of them to send that data? So you can send, that's for the load balancer, the GLP. right? And if one goes down, we'll just go back and just use the standby for everything. So the GLP, the gateway load balancing, is probably a good way of doing it, right? But we'll configure the HSP. If you type show standby, you'll see that this router is active because that means he is the one that's sending data to the outside world. If you see the word after you type show standby on the router and it says the state is standby, that means he's the one who is sitting idle, right? And the gateway load balancing protocol, like I said, which is good. Oops, sorry, we're coming to the last slide. Uh, GLBP, BP is the one that allows for load balancing, right? So we'll take a look at that as well. The configuration of both protocols are very, very easy. All right, so that ends the chapter, but we're not done yet. We are going to do a packet tracer. So if you would give me a second, I am going and to get a drink, and I'll be right back, and we're going to do a packet tracer. So don't leave. All right, I'm back. So let's continue. I told you not to go away. It's like as if you notice any difference. But anyway, so open up a packet tracer. So let's see what we can do. I'm going to open up, right? What I'm going to do is I'm going to go in and grab a 2960 switch, grab two of them. So put one right here, put another one right there. Okay, let's call this SW2. Call this hello SW1. Remember, you have to submit that. Let's go to the end devices and get two PCs. Okay. Let's just connect this PC to fast Ethernet 0 to 0, 1. This one is going to be fast Ethernet 0 to 0, 1. And let's put a trunk in there. This is going to be from 02 to 02, right? Now, let's assume that they are in the same LAN. So let's configure this guy. And you know what? Before I configure, let me just write down what this network is. Both of these guys are going to be in 192.168.10/24 network, right? So what I'll do is I'll give this guy the IP address 192.168.10.1, okay, /24. There's no default gateway. Let's go and give this guy 192.168.10.2 and /24, right? Now, because these ports are in dynamic ports, they immediately negotiated with each other. Well, let's see. Let me ping PC2. So if I type ping 192.168.10.2, I was able to reply. So I went through the trunk. Now, because these ports are a trunk, they immediately became well, they don't have to be a trunk because he's part of VLAN 1 and he's part of VLAN 1, so the data just went right over to the other side. Right? Now, if I go in and I put what happens if this link breaks for whatever reason? We're going to be in trouble. So what we're going to do is put another trunk in there. Let's use 03 and put 03 on this guy. Okay. So now because STP is running, they're negotiating. So this guy became the port. This guy became the, what do you call it? The primary link. One of them, by the way, is the root bridge, and one of them is not. And you know what I'm going to do? I'm going to set also, if this link breaks, that green one, the other one takes over immediately. So what I'm going to do is I'm going to bring in another switch, bring in another 2960 switch for redundancy purposes, and trunk them also here. So go from 04 to 01, give me another trunk from 05 to 02. Here I'll go from 04 to 03, and let's choose 05 to 04. Okay, and let's call that switch 3 on the bottom, SW3. So what you have right here is if a switch, any of the switches fail, you'll also have connections, right? So you'll have this guy goes to here, we'll get to the destination, or it can go through this switch if both of these links go. I have two different ways to get to here. And by the way, by looking at right here, can you tell me which one is the root bridge? By default is SW1. You see that? That's the root bridge because you see they're all green. They're all designated, right? So if I go to PC0, I can still ping a device. Now, if you go to the switch, go to switch 1. There's not a lot of configuration to do, by the way, with STP. And go to the CLI. Okay, let's just do EN like we always do, config T, no IP domain. Lookup, right? And just do Control Z, get out. Oh, we forgot to do a host name. You know what? Let's do a host name. Config T host name SW-1. Now do Control Z now, get out and type show spanning tree. Just do spanning tree. Okay, check it out. You see it says this is the root bridge. The priority number is 32769. Where did you get the 9? It's incremented by 1 because of VLAN 1. So the default is 32768 plus it was a negotiation for VLAN 1, so you added 1. So he's the root bridge for VLAN 1, right? And you can tell all the ports. 1, 2, 3, 4, 5, they are all designated, right? So you can tell. You see now which way the data goes. It goes from green to green, and then it can get to here. These two are blocking. So no data are traveling on these two ports no matter what. And so even if data is being sent out of here, they ultimately will go blocked here. And when it's sent here, it gets blocked here anyway. Okay, so here's what we're going to do. Let's make switch 2 as the primary, and switch 1 the root bridge instead of switch 1. And let's make switch 3 is the, you know what, let's put another PC on switch 3. We could do that too if we want. No, that's okay. So here we go. Let's go to switch 2. We're going to make it the root bridge by lowering the bridge ID number. So what I'm going to do is I'm going to go to this. I'm on switch 2. Do enable, config T, and you're going to say no IP domain lookup. And the host name is SW-2. Okay. And this is how you change the priority number. You say spanning tree for VLAN 1. The priority number is going to be 4096. Enter. That's it. Now they should be negotiating. See, this guy went to blocking immediately. And it's supposed to, he is going to be, if I go to the switch 2 now, do Control Z and type show spanning tree, he became the root bridge, right? And if I go to right here to switch 1, hit the upper key, he is no longer the root bridge. See, he has an alternate, one of the port became alternate blocking, which is this port, right? So now they're all green. So now he is the root bridge because I lowered the bridge ID number, right? That's pretty much it. When we get to lab, we're going to do a little bit more details. We're going to create some VLANs. This is just a quick demonstration on how STP works. Okay, now let's say I break this link. Just watch. So I take this link out for whatever reason. And now this port, let's see what happens. The original one for the root bridge should negotiate. Now data, which way is it going? It's being blocked still. Now, if I try to ping, let's see what happens. I hit the upper key and I'm pinging and I can't ping because you got to wait till it turns green. And there you go. See, it turned green and now it starts to work, right? It took over. See, the convergence, because you're running regular STP, was slow. If you were running rapid PVSTP, it would picked up immediately. So the data now goes through here. Now, what happens if I take this out? Another link out. Let's take that out. Now, one of these have to open up. I mean, we don't even have to get into that. And if you wait, now the negotiation, see the convergence time takes a long time for that to happen. Okay, let's just wait till it turns green and you should be able to ping. Let's see. Let's force a ping. There you go. See? They negotiated and this guy now turned green and a bingo. Took even longer to negotiate. All right, let's bring back the trunks. By the way, you don't have to do any trunk. We'll talk about that in class. When we do the trunks, we should, with the native VLAN and all the goodies. Okay, now leave that alone. Now, what happens if they want to go to the outside world? So let's bring in a router. Let's bring in a 2811 router. Okay. And let's connect that router to Fast Ethernet 00. Let's connect it to switch 1, Fast Ethernet 06. Right? And okay, but we're back to normal between these two. So let's make the default gateway. What did we hear? The default gateway, let's make it 192.168.10.254 because it's the last address in the network, right? And let's make sure PC2 has it too. Excuse me. 192.168.10.254. Okay. Then I go to the router and say new. I type enable config T host name R1 and you're going to say no IP domain lookup, right? And we're going to go to the interface fast Ethernet 0/0 and we are going to say what? We're going to say IP add 192.168.10.254 with subnet mask 255.255.255.0 and of course no shot. So now that's the default gateway. They should be able to get out to the outside world, correct? If this goes down, they can't go to the outside world. Here's what I'm going to do. I'm going to add another router up here and add another router right here. You know, the first thing we should always do, by the way, go to the switch one here. I want you to type copy, run, start. Because if we ever turn these off and hit enter twice, we're in trouble. Go to switch 2 and do copy, run, start. Enter, enter, enter. Go to the router that we just created, Control Z, and do copy, run, start. Okay, so now the running configuration, what I just did, is in the NVRAM. Okay, because what I want to do is I want to turn off the switch. I got to put in serial ports. And you know what? Put another PC. Let's put another PC out here someplace. Okay. Okay, here's how we're going to connect this. Turn off this. Go to the physical. Turn off the router. And put a WIC2T in there. Turn it back on. Go to this router. Turn it off. Put a WIC2T right there. Turn it back on. Close it. Oops, I got to go to this router. Turn it off. And put a WIC2T in there. And turn it back on. All right, now I'm going to make router 1. Actually, this is R1. Make this R1. Make this R2. And this make R3. Taking too long just to show you how HSRP. We're going to have this as a standby router, R3. But anyway, so let's go, and we're going to make sure that R2 is the DCE. So always S000 to S000 of R1. Get another DCE cable, go from R2 to 0001 to R3 000. All right, get a straight through cable from R3 fast Ethernet 0 to the switch 06. And let's go to another from PC2 fast Ethernet to, oops, oh, that's no good. We don't want fast straight through. It has to be a crossover, right? Crossover, because it's directly connected to the fast Ethernet interface of this router. Okay? Okay. This is not a default gateway. We'll talk about that later on. Let's configure the links. So let's say this link right here is going to be network 10, 20, 30.4/30. And this link right here, let's make it 10, 20, 30.0/30 network. And let's say this PC should have the IP address 172.16.100.1 and leave it as /16. Its default gateway is going to be 172.16.100.2. Okay, that's his default gateway. Okay, let's go to R2 and configure it. Okay, so we go to R2, go to CLI, say no, and do enable, config T, no IP domain lookup. Okay. And a host name of R2. You go to interface fast Ethernet 0/0 and you give it the IP add 172.16.100.2, 255.255.0.0, and a no shot, right? I go to interface serial 000, which is this interface right here. I'm going to give it the IP add 10.20.30.5, right? The first address in that subnet. Space 255, 255, 255, 252. Clock rate of 64,000. Got to spell clock correctly. And then no shot. Then I go to the other interface, serial 001, and I say IP add, and then in 001, it's 10.20.30, right? IP add 10.20.30.1, 255, 255, 255.252, and a clock rate of 64,000, and a no shutter too, right? So we're all set right here. Why is this interface up? Let's see, what IP address did I give it? Show run. How is that past Ethernet 00 configured? It have no IP address, but it's been up already. Oh, we got to give it an IP address. So go to R1 and do config T. Go to interface serial 000 and type in IP add 172. Oh no, 172. It's 10.20.30. The other one got 5, so this guy should get .6. Space 255, 255, 255.252. And just type a no shutter. Okay, I go to router 3. I am going to go in and say no. And type interface serial 000. Oh God, config T first. And then I go to interface serial 000. And I say, what are you kidding me? EN, config T. Then I go to interface serial 000. And then I say IP add 10.20.30.2 because the other one got the .1, right? .2 space 255, 255, 255, 252, and the type no shot. Okay. Okay, so far so good. Now what I'm going to do is I'm going to choose this interface, and this guy got 254. Let's make it 253. Okay, I want him to be in the same LAN as the other two, the PC, same LAN as this PC and the other PC. So if I go to interface fast Ethernet 0/0, and I give it the IP add 192.168.10.253 space 255.255.255.0 and type a no shutter. Okay. Now we'll wait till this turns green. The problem is now the default gateway that I gave these PCs is 254, right? These two PCs, correct? 254. So they'll be going through this interface to get to PC2 if they want to ping this PC2, which is 172.16.100.2. But we have to have some routing protocol between them, right? So what I'm going to do is I'm going to do just, I don't want to run I could run static routing. Let me just do static routing, right? I'm going to do a default route, the router 2 out of here, and a default route out of router 2 here, and then a default route. Oh God, yeah. Then I have to come back there. Let's just do a default route this way. I go to R1 and say IP route everything. Whoops, I'm not writing. Config T, config T, and I'm going to say IP route 0000 space 0000 space serial 000. So now everything is going to go out of here, and I'm going to come back to this router, and I'm going to say, you know what? Instead of doing that, you know what? Let me take that out. Take that no IP route. Let's do OSPF between these two routers. Here, I'm going to go to router 2. We're going to do OSPF. Let's start with router 1. I'm going to say router OSPF1 network. I'm going to advertise the network, which is this network, 192.168.10.0 with subnet mask 0 wildcard 0.0.0.255 area 0, and I'm going to advertise network 10.20.30.4 with a wildcard of 0003 area 0. All right. Forget about that. Let's do passive interface on the fast Ethernet 0/0. Okay. So that's OSPF is done right here. Do Control Z, copy, run, start, just in case. And let's go to router 2. Okay. I'm going to exit. I'm going to say router OSPF1. And I'm going to say network 172.16.100 dot, I forgot what I did, dot 100.0, right? Yeah, let's do dot 0. What the hell? Dot 0 slash 24 slash 26 16, I'm sorry, 255.255 area 0. Okay, network 10 20 34 0003 area 0, and then it should now communicate network, and the other one is what, 10 20, there you go, it worked, good. Network 10 20 30.0 with 0003 area 0. All right, let's do a passive interface on the fast Ethernet 0/0. All right, now I go to router 3, type exit, and you say router OSPF1 and network 192.168.10.0 with 0003, not 255 because it's slash 24, right? Oh, you got to write area 0. And then we're going to do network 10 20 30.0 with 0003, right? Oh God, keep forgetting area 0, and then you do the passive interface on the fast Ethernet 0/0. Okay, so if you do Control Z and oh, this is wait, config T. This is and say host name R3. We forgot to do that, and I probably did not do domain, no IP domain lookup. Right? I do Control Z, copy, run, start, enter, enter. Right? Now, let me do copy, run, start on R2 just to make sure. Control Z, copy, run, start, enter, enter. Now, if I do here, let me go to PC0, and I want to ping the 172.16.100.1, which is this guy, I think, on the top. Isn't that .1? I think so. 172.16. Let's see. It's being timed out. There's some configuration that we did incorrectly. 172.160 I wrote. Ooh, that's not wrong. That's not right. So there you go. Fixed it. See, I did that on purpose. All right, let's try the thing again. It's supposed to be hit the upper key, hit enter. It's supposed to be 172.16.100. All right, there we go. Now we are replying. So I'm looking for, okay, so if I repeat again just to make sure everything's doing good, and now here we go. We got all the packets being. By the way, we are going this way, and PC1 also should be able to ping 192.168. What the hell am I doing? 172.16.100.1, right? And he should be able to reach that guy on the other end too. But remember, his default gateway, both of these guys, if you remember, their default gateway is the .254, right? Which is this guy. So he goes in and he ignores this router and goes this way. And he goes in and he ignores this router and he goes this way too, right? Now, if anything goes wrong with this link, they're screwed because they're told their default route is here, right? So what we're going to do is we're going to say to the router one, we're going to run a virtual router first, and we are going to say you are going to be the standby, he's going to be the standby, and he's going to be the active router. So if this link goes down or the router goes out of business, both of these guys will come back and use this router to get to PC2, right? So let's go to R1 and do config T. Go to the interface, fast Ethernet 0/0. This interface right here. We're doing HSRP, right? You're going to do standby, group 1. You got to use a group number, okay? And let's assign group the virtual interface IP. It's supposed to be in the same subnet as all of these guys, which is 192.168.10. Now we chose .254 for this guy. We chose .253 for this guy, right? And this PC1 is .1.2. So let's choose 252, right? This is 54. The other route is 53. So this is 252. Okay. And then you're going to say you got to give it a priority number that is higher than 0. and let's say it's 150. Okay, and then you're going to say preempt. Okay, that means he became active. Now, if you go to the other router and then you do config T and you go to interface fast Ethernet 0/0, okay, and then you say IP, I'm sorry, standby, the IP, standby group 1, the IP address is 192.168.10.252, right? That's all you have to do. The other one is 252, I said, didn't I? Yes. Don't put a priority number or preempt. The preempt means just delete everything else. If there was any priority numbers, get rid of it. Just if you make a priority number 150, he's going to become the active. The other one is going to be the standby. You see, now he is standing by. If you type Control Z and you type show, well, first of all, by the way, you got to go to the PCs before you even do that and change their default gateway to 252 to the virtual interface, to the virtual default gateway. So go back to this one and make sure it's 252. Okay. Now they're pinging, they'll still be pinging through PC2, through R1. Now, when R1 fails or the link fails, because now we have a virtual interface on both of them, he becomes the active and they'll start pinging through here. Okay, so if you go to R1, first of all, do Control Z and type show standby. And it shows that this is the active interface, right? If you go to R3 and type show standby, it shows it is standing by. So let's do some testing. Go to PC0 and let us ping .1. It replies, right? If you go to PC1, you hit the upper key, it also replies. By the way, you can do tracert. Let's do tracert. Tracert 172.16.100.1. You see it's going through the .254 router, right? This router, a .254. This PC goes through this .254 to reach PC2. Now, here's what we're going to do. Remember, he's the standby and he's the active. Let's say this link went down. So, bingo, gone. I lost my connection. Now, these guys should be going through R3. So if the router or the link breaks for whatever reason, if you go to R3, look, it became active. You see that? So if you type show stand by, bingo, it became active. So these PCs will never lose. Now, if you go to PC1 and do tracer again, now you watch, you're going to go .253, which is this interface now you're going through. So if I hit that again, bingo, see, I was able to ping. Now you can actually ping it too, of course. 172.16.100.1, you'll be able to ping because now you're using this router to go through. So HSRP allows you to allows one router to stand by just in case the other router fails, which is great. The GLP, by the way, you can do GLP and it will use both to send data through both links to get to PC2. So this way for load balancing, the configuration is the same thing. We'll do that in the lab when we get to class. All right, so please make sure you save this and you submit that along with the other couple of questions that I asked. I know this is a long chapter, but that's what it really comes down to. Chapter 1 was a little bit easier, I guess. Okay? All right, so keep up the good work. Make sure you read the chapter, and when we come to class, we're going to do a little bit more of hands-on. All right? Until then, until chapter 3, God bless.